Yeah, camps on your own. Let's start off. The last thing that we did was Lloyd's mirror. Next thing, like I said, there are a few experiments. The next one is Fresnel biprism experiment. This is again, they're important for your HSC boards also, and it is also there in HSC, NCERT as an example problem. So they would just give you the direct, numbers and everything, and they'll expect you to solve. You need to know this. So Fresnel biprism experiment. So we take a biprism. So basically it is called biprism because it looks like an upper one and the lower one are like two prisms. We have a screen here. This is angle A and this is angle A. This is the object. So the light rays which hit this thing, there will be deflection in a prism. So this will act like one image. And the light rays which are hitting the lower part of the prism will bend like this. That will act like another source I2. This distance is A and this distance is B. So basically this I1 and I2 will act like two coherent sources, and from there we get our YDC experiment. So here it's a thin prism. If you remember, we did this in ray optics. Thin prisms are where angle is less than 5 degrees. So the deviation delta is given by A into mu minus 1. So listen to the derivation. So there are certain approximations they have taken. So the deviation is delta into mu minus 1. So if this light ray had gone straight, this would be your deviation delta. Now here, if you take exactly the line in the middle, a bisector, this angle is delta by 2 and this angle is delta by 2. So this is also delta by 2. And here they have chosen this I1, IS, and I2, all three are on the same vertical line. So that is an approximation. So why the source should be there? So that is the thing. So we take the images to be exactly on top of this thing. And then you can clearly see, and this distance will be A. Since the lens is very thin, you can assume that distance is almost A. This distance becomes A tan delta by 2. This distance also becomes A tan delta by 2. So this whole setup works like we have two sources now, I1, I2. This is the screen here. And this would be the distance between them, small d, where d is nothing but 4 times A tan delta by 2. Since delta is small, you can approximate this to be 4A delta by 2, which is 2A. Delta is nothing but A into mu minus 1. And this would be your capital D, which is nothing but A plus B. So from here we get fringe width. So basically you can measure the fringe width on the screen, and using that you can actually measure the refractive index of the prism, lambda capital D by small d. That will be lambda capital D is A plus B by 2A mu minus 1. Exam में this is a problem. They'll give you A, B ka value and mu ka value and lambda and A, and they'll ask you fringe width. Now, if you don't know what is the experiment, you won't be able to solve. And this is there for HSC derivation, 4 marks. if you're in HSC boards. NCERT is an example problem. So it's important one way or another. That is your Fresnel biprism experiment. So the writers get deviated by delta, and you take the image I1, I2 exactly on top of the source. If you know these 2 points, you can derive it. It won't take much of a time. Clear with this? Next one, Quincke's tube. That's your third one. If you see all these terms, right, Fresnel, biprism, Lloyd's mirror. So like I keep saying, the terminology is more important. At a mains level, questions will be straightforward, but because you don't know the terminology, people leave the questions and come unnecessarily. Next thing is your Quincke's tube. So Quincke's tube is an again experiment to find speed of sound. This is the third experiment to find speed of sound. Anyone remembers what are the first two? Resonance column tube and Kunz tube. There, what is the concept we used? We used stationary waves to find the speed of sound. So here, Quincke's tube is an experiment to find speed of sound using interference. So let me show you how the picture will look. And this is the setup. You can see the setup how it is. Like you have a tuning fork here, frequency F. So you have one pipe on the left and one pipe on the right. And the right side pipe is a movable pipe. So when you move the right side pipe, you can actually increase the distance traveled by the wave in one thing. And the actual picture would look like this. There. This is how the setup would actually look in real life. A Quincke's tube. So it's made of two rods and one rod is movable. So how does this work? Again, a pretty straightforward concept. But again, when they say Quincke's tube, you should know how it works. So one sound wave will go from the tuning fork. Let's say it will go from the left. Another sound wave will go towards the right. So there we got two sound waves. Now, since the right side is movable, let's say if you move this by distance x, if you move this by distance x, then the bottom part also moves by x. That means whenever you move the right side by x, what is the extra path that you get? 2x, isn't it? You're making the sound wave on the right hand side travel 2x more. So that is how you create a path difference. In the pipe on the right. ADC moves by x. Sound wave travels extra 2x. That you should know. Exam, they won't tell you all the story. Therefore, the path difference is equal to 2x and is equal to n lambda for nth maxima. So basically, let's say initially both are same distance. You will get a maxima. If you pull it, then what will happen? Sound will decrease, then again increase. Sound will increase and decrease. So the question would be like this. When it is pulled by 2 meters, the person hears a 10 times maximum sound. Matlab it's the 10th maxima. So from here we get lambda is equal to 2x by n. Speed of sound is f lambda. बस हो गया इतना experiment था. Let me show you a question how they'll frame. I think it's straightforward, but the moment you hear the word Quincke's tube, you're like, what? People don't have an idea about the experiment and you'll goof up. If you know actually the whole thing, it'll take barely 30 seconds to solve the question. Let's see an example on this. Clear? Let's see a question. In Quincke's tube. An observer hears max sound 5 times. When it is moved by 2 meters. What did you move? That you should know. If you have no idea what did you move, why did you hear 5 times, you will now have no clarity if you don't know the experiment. The frequency of the tuning fork is 400 hertz. Find the speed of sound. Get it, easy one. Yeah, right, yeah. नहीं परोजा. Right question. See, so what is the path difference? If you move it by 2 meters, the path difference will be 2x. 4 meters is the path difference. You're hearing 5 times the sound, so delta x is equal to n lambda. So here n is equal to 5, since you hear 5 maximas. So 4 is equal to 5 lambda. So lambda is equal to 4 by 5 meters. Speed of sound is equal to f lambda. 320 meters per second. Easy? That's your Quincase tube. Any doubts on this? Yeah, most of you got it. Next thing, Bragg's law. So what is this Bragg's law? This is an interference. Did you ever think about this? They say in a so-and-so metal, the bond distance between the two sodium atom is 1.5 angstroms. And this thing, how do you measure such a small distances? How do you measure bond lengths in lattices or in atoms? You don't have any instrument which can measure small distances. We actually use interference. So interference using X-rays. We use X-rays because X-rays are very small wavelength, like 1 angstrom or half angstroms, to find bond distance and bond lengths. So we have a lattice. They're all equally spaced, so the distance is d between them. So when you send a light ray, so we have a reflection of a light ray on the first layer and the reflection of light ray on the second layer. You're sending parallel beam. So this is a reflection on first layer. This is the reflection on second layer. Since both are getting reflected, both will have a phase shift of 180 degrees. So that won't matter. But if you look at this red one, do you agree this distance and this distance are equal? The problem is the shaded one, which I'm shading in black. This is the extra distance the red one will travel compared to the green one. This is your extra path. Now, if I take angle theta with the vertical, sometimes they'll give it the horizontal. So be careful. This is theta. So this guy will be, and this bond distance is how much? This is d. So this will be d cos theta. So path difference delta x will be 2d cos theta. This will be equal to n lambda for maximum. D is equal to n lambda by 2 cos theta. For n is equal to 1, if you take first maxima, You get the bond distance will be lambda by 2 cos theta. Lambda is the wavelength of the X-ray and theta is the angle which you are incident. You know everything. This is your Bragg's law. This can be asked in interference. This can be also asked in X-rays, which comes in modern physics. These are the 4 main things in this chapter, wave optics. Bragg's law, Fresnel biprism experiment, Lloyd's mirror, and Quincke's tube. You should know your terms. In waves, how many are there? Kunz tube, sonometer, and resonance column tube. Those are the 3 main ones. Ray optics, how many are there? Lens displacement method, yeah, that was the most important thing. Lens displacement method, that was the most important. That's an experiment actually. That was the main thing. And then Newton's law of lens, Newton's lens formula. Those are also some formulas. They're not an experiments, but there are formulas there. Prism to hai. The whole prism stuff is actually an experiment only, if you remember. The deviation and everything, that whole result is this thing. Remember the result, refractive index ka anyone? Mu is equal to sin A plus delta m by 2 by sin A by 2. That parabolic graph jaisa lagega ek. That whole thing is an experiment. So yeah, that's your Bragg's law there. Next thing, optical path. Now this is a third thing. If you remember at the beginning, I told you there are 3 ways you can create a path difference. 1, make them travel different distances. 2nd, reflection. 3rd, make it go through a medium. So what is this optical path? If 2 light rays take same time to go from point A to point B, they're said to have same optical path. If you remember, we learned this in ray optics, Fermat's principle. Light rays always choose a path of least time. That means if 2 light rays are going from A to B in 2 different paths, both the paths must have taken same time. If 2 paths have same time, then the light ray will choose both the paths. The light will split. So optical path, simply, right, it is based on time. It is not based on distance. For example, let's say when you're going from Ghatkopar to Colaba, and let's say there is one route through Eastern Expressway and one through some everything. And if both of them take 40 minutes only, it doesn't matter which path you take, isn't it? But then you will take the shorter one because to save fuel. But light has no concept of fuel and also it doesn't care. It will take both. And best example, you have seen this before. We have seen this in lenses. Think about it. When you take a lens, if this is your object, the light ray is going straight through this. And let's say this is the image. If you take another light ray, this actually goes like this. If you take another light ray, it goes like this. Now, when you say image, right, understand one thing. How do you get an image? 2 light rays from the source meet at the same point at the same time. Tell me one thing. If the red one comes first and green one comes later, do you think you'll get an image? That means all these 3 light rays are taking the same time to reach, but you can clearly see the black is traveling more. So what is the catch? The catch is, if you remember the speed of light in medium, it is actually C vacuum by mu. Light travels slower in a medium. So when you take this lens, even though the red one is traveling less, you can see this is more thick, isn't it? You're making the red one travel more distance inside the lens, whereas this black one is traveling less distance inside the lens. So even though the red travels more, it slows down a lot inside the lens, the red one. So overall, the time taken will be the same. Clear with this? So this is the best example. In a lens or even in a mirror, whenever the light rays reflect from source to the image, all the light rays that are going from source to the image will have same optical path. They should meet at the image at the same thing at the same time. Yeah, we use the Fermat's principle to prove law of reflection. So here, if you see all rays take same time. from O to Y. So they have different geometrical lengths, but they have same optical paths. So optical path is mostly based on time rather than length. It's like when I say light year, when you hear that word, what does it give you a feeling of? You think it is based on time, but actually it is a length ka measurement, something of that sort. So they have different geometrical length, but same optical path. There. So someone tells you what is optical path, that is how you define. If two light rays take same time to go from A to B, they say are said to have same optical path. That's it. Straightforward definition. Let's see a question based on this then. Let's say we have an interface, a curved interface. The right side is mu2, the left side is mu1. It's not a length, it is just one interface there. You sent parallel light rays, so they're coming from infinity, and they all meet at the focus, f comma 0. So when you send a parallel beam from infinity, so technically when they're coming parallelly, they're traveling same distances, isn't it? When they hit this interface, they all converge at this point f comma 0, and mu2 is greater than mu1. Find the shape of the interface. Don't say it's a parabola. That's for mirror ka reflection. This is not reflection. And this is not a lens. Lens mein there are two refractions. Find the shape of the interface. Options will be circular, parabola, hyperbola, ellipse. Again, just to give an idea, just now I taught you. All these letters are parallel means they're starting from the same source. That means when they reach the focus, they should have taken all same time. Make sense? But you can clearly see everyone is traveling different distances. They're traveling different distances, but they all reach the focus at the same time. What is the shape of that interface? Try. This will be a proper advanced question. And the concept is pretty simple. Time taken is same. It's basically little kinematics. There's nothing more. Let's see how will you handle this. Try 2-3 minutes, then I'll show you. I can even find the equation of that interface. You solved it so fast, Rams. Right though. Right, Aditya. You also solved it so fast. Guess mara kya? Didn't solve guess mara. Solve. Because if I say mu1 is less than mu2, answer change ho jayega. So you need to know what is the equation there. Okay. let me give you a few data points. See. Forget about all these things, just take two light rays. Let this point be x comma y. Now you can clearly see till this point, right? They're traveling same distance, agreed? The problem starts from here. A, B, and this is F. So A to B and B to F, the green one. So can I say like this? Time taken to go from A, B, F must be equal to time taken to go from O to F. Wasn't that the whole point? So when you're going from A to B, F, so A to B, but what is your speed? You're traveling in mu1 medium. So this is AB by mu1. This is BF by C by mu2, just speed changed. This O to F is anyway traveling only in mu2 only. Clear with this? Substitute AB, BF, F in terms of X and Y. Solve. I'll give a minute or two. If you wrote this, you're done. Physics part is over after once you wrote this statement. The time taken to go from ABF must be equal to O to F. That is the whole point of optical path. Because before A, they are parallel, so they travel same distance. You didn't have an issue. So from here, if you drop the perpendicular, this will be Y. This will be F minus X. This will be X. So this will be mu1. AB is simply X. This is mu2 root over, that's a Pythagoras theorem there, root over y square plus F minus X whole square. This is mu2 F. Send that mu1 X that side and square it on both the sides. You'll get mu2 square y square F minus X whole square. This will be mu2 F minus mu1 X whole square. Expand this. This will be mu2 square y square mu2 square F square mu2 square X square 2 mu2 square Fx is equal to mu2 square F square. This guy and this guy are gone. Bring all x terms to one side. That will be mu2 square minus mu1 square X square plus mu2 square Y square minus X into 2 mu2 square F minus 2 mu1 mu2 F is equal to 0. If you see this carefully, right, I can actually adjust this. I can write something like x minus h whole square by a square plus y square by b square is equal to 1. Can I do that? So you can clearly see here, if mu2 is greater than mu1, it's actually an ellipse. The coefficient of x square is positive. If mu2 is less than mu1, then this will become a hyperbola. No? If the quotient of x square is negative, you will get something like 3y square minus 4x square is equal to something. Isn't that a hyperbolic equation? Clear with this? That would be the equation, but yeah, that is how you prove it. Any doubts on this? Again, what did we do? We simply said time taken is same. That's it. We didn't use any out of the world concepts. Optical path. That is how they'll frame questions on this. So clear with this? So some people will say, sir, can I use, refraction on curved surface का formula, that mu2 by v minus mu1 by u is equal to mu2 minus mu1 by r. The problem with that formula is you have assumed this is a circle, isn't it? The moment you say r, didn't you assume it is a circle? That is a problem. So if you use that formula, you will not get an answer because you're assuming it is a circle, and this is not a circle. There is a different radius of curvature at every point. Clear? So you can't use this, you can't do this with ray optics. And if you remember, that formula is also derived for what? For paraxial rays. And here, if you see, you're talking any light ray will still meet at the focus. So these are not paraxial rays, and you can't, this is not a circular thing. So your ray optics is out of the question here. Okay. So when you see this, you get a feeling, na, first thing when you see this question, you'll feel like, this must be ray optics question. But when they use the word find the shape of the interface, that should give you a clarity, boss. This can't be a circle. If it is a circle and if the rays are paraxial, then ray optics would work. But again, if you remember, ray optics, all formulas are approximations. That is one. Next thing. Let's say we got a slab of distance d. This is mu slab, and let's say the medium outside is mu m. This is an important thing. Now, if a light ray goes inside the slab, the speed of the light ray is c by mu s. So the time taken will be d by c by mu s. So I want to replace this, right? So if you put a slab in a medium, right? I don't want to deal with slabs. I want to know this slab is equivalent to how much medium. Meaning, if you replace this slab with a mu m medium, d dash, and if you send the light ray, I want the time to be same. So here the speed is c by mu m. So here the time will be c by d dash by c by mu m. So if you say both of them have same optical path, then it will be mu s d is equal to mu m d dash. So we get a d dash is equal to mu s by mu m into d. If outside medium is vacuum, then it will be mu s into d. What is the meaning of this? A light ray which is going inside the slab will feel as if it has traveled a distance of d dash in the medium, isn't it? The time taken for a light ray in a slab is equal to the time taken for a light ray in a medium. This distance is d and this is d dash. So this is something like, a equivalent length for a slab. You can replace the slab with this much distance and you can solve the problems. Clear with this? So exactly what is happening here? Why does it feel like it is traveling more? Think of it like this. Suppose if you actually have a slab, if you remember, the speed of light decreases, so wavelength also decreases. So if you have a wave, the moment the wave enters inside, it actually becomes something like this. It gets compressed. Here the wavelength becomes lambda by mu. The same wave, if you are going without the slab, now see if I count them, what will happen? Let's say this is 1, 2, 3, 4, 5, 6, 7, 8. This is 1, 2, 3, 4, 5, 6, 7, 8. Did you see what happened? Even though both the light rays are parallel, didn't you still create a path difference? Because you went in a slab, you slowed down. So it started feeling as if, you have traveled maybe more distance or less distance. You still got a path difference because of the slab. Are you getting the difference? This is what is happening when you go through a slab. Even though they're traveling, same length, because the upper light ray is slowing down in a slab, its optical path will be different. So this is the main result we have to use. So let's say if I'm sending one ray 1, let the surrounding medium be mu m. Let the distance be d. So if you replace this with a slab, so if you put a same slab ka length, now if you send a ray 2, So what will Ray 2 think? Ray 2 will think it traveled mu s d by mu m while going through the slab. So that is what Ray 2 will think. I'm traveling this much distance. If the slab had not been there, you would have traveled how much? You would have traveled d. So because of the slab, you got an extra path difference which is mu s d by mu m minus d, which is the thickness of the slab into mu of the slab by mu of the medium minus 1. You definitely need to mark it up. This is the third way to get a path difference. Whenever you go through a slab, because you slow down in a slab, again, depends on mu s and mu m ka value, right? The light ray will feel it has traveled this much extra distance. Is this making sense? Once you know this, you can handle most of the questions now. If the slab was not there, you would have traveled d. Because the slab is there, you traveled mu s d by mu m. So this, because of that slab, the light ray will feel this is the extra distance I traveled. Clear with this? There's a third one, everyone. First thing, make them travel different distances. So same medium, you're making them travel at an angles. Second thing, reflection. Third thing, slabs. These are the three ways you can create path difference. Let me show an example. How will this affect our problems? Again, in every question, I keep saying the same thing. You just need to find the path difference. This is just another way to create path difference. Every other result you learned in YDC will be still valid. So let me take an example and let's see. So we have two slits. We got a screen, S1, S2. You keep, normally they use mica sheets. They'll say thin mica sheets are used. T1, mu1. The sheets must be thin because if the sheet is thick and if the light ray goes at an angle, then should it take this distance? It becomes a problem. We can't calculate that because it depends on the angle of incidence and everything. So we take the sheets to be thin, so we can assume it to be T1 only. This is point P. This is y is equal to 0. This distance is y. On top of it, this whole setup is immersed in a medium. I am messing it up as much as possible. So this whole setup is immersed in a medium. And now you want to find the path difference at point P. So if you know how to get the path difference, your job's done. So listen carefully. It's not tough if you got this. And I don't remember this result. Every time I get this, I derive. T1 and T2 are thickness of the slabs. The thickness of thin slabs. Mu1 and mu2 are refractive indexes. So you want to find the path difference, delta x. So light ray is going from S to P. S2P, great. But since you went through the slab, you will feel you traveled extra distance. How much? Thickness of the slab, refractive index of the slab by refractive index of the medium surrounding, -1. Does that make sense? That would be the extra term there. Minus S1P, because you went through the slab, T1, mu1 by mu medium, -1. That is the second thing. Isn't that your path difference? That's it. Then S2P minus S1P plus T2 mu2 by mu m -1 minus T1 mu1 by mu medium -1. And what is S2P minus S1P? dy by capital D. That formula is still valid. This is the path difference at point P. So what do you want to find? You want to find the central maxima? For central maxima, delta x is 0. If you put delta x is equal to 0, you'll get y is equal to capital D by small d, t1 mu1 by mu medium minus 1 minus t2 mu2 by mu medium minus 1. This is the shift of central maximum. Matlab it's the shift of the entire pattern. So whenever you keep slits in front of this thing, what you're doing, you're shifting the whole pattern up or down. So they'll ask a simple question like this: what distance the central maximum shifted? Now, if you can remember this, great. You can't remember this, it won't take much of time to derive also. But this result you have to mug up. Without this, you can't go ahead. And what about the fringe width? Do you think the fringe width will change? Lambda capital D by small d, nothing changes. So fringe width is unaffected. So putting the slabs in front of the slits will not affect the fringe width, it will just shift the pattern. You want nth maxima, delta x is n lambda. Like I said, once you got delta x, you will get everything that you want. Have a look at this example. This is what you do. In YDSC, you have slabs. Yeah. Let's see. Now you guys do this question. This whole region is filled with medium UM. This would be a simple mensural question. Find the relation between T1, T2, mu1, mu2, and mu medium if the central maxima does not shift. So central maxima is at y is equal to 0 only. Find intensity at point P. Let's see the first one. This is how I do. There is actually another faster way to do. I'll show you normally how I do. One path difference. So the letter is going from S2P and S1P. Like literally what I derived, I'll write the whole thing again. S2P plus T2. You're going through a slab. So mu2 by mu medium minus 1. This is the light ray from the bottom. S1 plus T1 mu2 mu1 by mu medium minus 1. This is the path difference. S2P minus S1P will be nothing but dy by capital D. Now you're saying central maxima does not shift. So central maxima meaning delta x is 0, does not shift mean y is also 0. So this will give you T1 mu1 by mu medium. At a mains level, generally, they don't put that medium, they just put vacuum and then keep only generally one slab. This is the relation. There is a faster way to do this. This is what I'll do in the exam. At the central maxima, normally, if the slabs are not there, S2P is equal to S1P. Agreed? That means the reason why it is not shifting is because whatever shift is due to this slab, this is also shifting the same amount. Means both the shifts are equal. So T1 mu1 by mu1 minus 1 is equal to T2 mu2 by mu1 minus 1. Bas ho gaya, direct answer tha wo. You can argue like that and finish up without writing all the story. Is that making sense? Because S2P and S1P are already equal at y is equal to 0. And you're saying there is no shift. Matlab, each slab must have shifted them by same distance. So they must have been equal. And what about the second thing? You can leave it there. Second one, there's nothing there. I just wanted to show you one thing there. You got the path difference, you need to get the phase difference. 2 pi by lambda delta x. You know already delta x, na? Sub value substitute kar lena, you'll get the answer there. I need to give y also, na? Let's say y is equal to 3 mm. It doesn't matter. So the catch is this and this. What is this lambda exactly? This lambda is in medium. You're taking the light rays in a medium, so the path difference is in the medium. So lambda also must be in the medium. But in the question, they gave lambda vacuum is 6,000. That is a mistake. So everything else you'll get, you'll mess up the lambda and come. So lambda medium will be lambda vacuum by mu medium. But that you have to take care. If you got that, then you're done. So intensity is nothing but 4i cos square 5 by 2. Once you got your delta x, you will get intensity. That's not a big deal. All those numbers are given, you can dump them and finish it off. Okay with this? Let's see the next one. I'll mix up everything. If you got this, then I think you'll understand YDSC everything. Any doubts on this? Let's see the next one. The source is not in the center. Remember this question? This is D1. This is D2. This region on the left-hand side is filled with mu3. This region on the right-hand side is filled with mu4. I messed up the medium on both the sides. This is a good one. This will be a good advanced question. Find intensity at point P. Basically, I'm asking path difference at point P. If you got delta x at point P, you'll get it. Let's see how will you handle this. And lambda vacuum is lambda naught. you know what to do when there are slabs, right? You know what to do when the source is not in the equidistant. You know when there is a medium. And if there are two mediums and slabs and the object is shifted, I messed up everything there. Let's see, think for 2 minutes. Then I'll tell you how to approach this. If the whole thing had same medium, your life would have been easy. Because you're messing up the medium, it becomes confusing. Think. Let's see. The issue here is because the light ray is going through two different mediums, when I take delta x, can I really just directly subtract them? The mediums will mess it up. So problem ye tha. It is like, see, if I ask you this question, which is greater, 3 apples or 2 oranges? You're getting the problem here. But let me ask you this way. What is the cost of 3 apples and cost of 2 oranges? Now can you compare? So we need to bring them to something common. So what we will do, let's calculate all the path differences in vacuum. So whatever path difference you get, for example, see, if you go through a slab of mu, remember this is equal to a vacuum of mu into d, na? So let's convert everything into vacuum. That is the catch in these kind of questions. Whenever a light ray goes from different mediums, convert everything into vacuum, the path differences. Calculate all path differences in terms of vacuum. You can actually choose mu-m also. You can choose mu4 also, but convenience. I don't want to get confused. I will keep normally vacuum. That is the main theme in these questions. Once you figured that out, then things will fall in place. Let's see. So one light ray will go like this. Isn't it? The light ray will go from S1P. Another light ray will go from S2, S2P. Isn't this the two light rays? SS1P and SS2P. Now listen carefully here. So the path difference delta x. First thing, you're going from S to S1, great. But in which medium are you going? You're going in mu3. So in vacuum, what will it become? It will become mu3 SS1. Makes sense? You just have to multiply with mu in order to convert anything into the vacuum. SS1 is the distance in a slab, isn't it? If you want to replace this with a vacuum, then it will become mu times d. Making sense? Because formula देखो ना यहाँ पे what we got, mu SD by mu m, isn't it? If you're comparing this with vacuum, outside is 1, isn't it? Mu medium is 1. The mu of the slab into d. So that is how you convert part differences. Multiply with mu medium. To get optical path in vacuum. Then you're traveling in which medium? Mu4. And then what is optical distance? S1p plus, but because you're going in a slab, you'll get T2 into mu2. I got that is T, wait. I wrote for SS1 na? ठीक है. T1 mu1 by mu4 minus 1. Is that making sense? So this term in the middle, what you have, this is the path difference in mu4 medium. By multiplying with mu4, you're getting it into vacuum में convert कर लिया. Is that making sense? You just multiply with that particular mediums and you'll be done. And this whole thing minus, now this will be mu3 SS2 plus mu4 S2P. I should have written reverse, but ठीक है. This will be T2 mu2 by mu4 minus 1. So from here we get delta X will be mu3 SS1 minus SS2 plus mu4 S1P minus S2P. ठीक है. I should have written minus plus, but then mu4 T1 mu1 by mu4 minus 1 mu3 wait mu4 T2 mu2 by mu4 minus 1. That's your path difference, everyone. And we already know what is this thing. What is SS2 minus SS1? That would be nothing but dx by d1. This we did before. And what is S2p minus S1p? That is dy by capital D2. You know everything there, isn't it? So what is this delta X? This is your path difference in vacuum. You have converted everything into vacuum terms. And delta X must be equal to n lambda vacuum. Because you converted everything into vacuum, lambda also must be in vacuum. You want phase angle? 2 pi by lambda delta X. You want intensity? 4 I naught cos square phi by 2. Like I said, once you got the part difference, you'll get everything. You know everything here. You know dx, d1, d2, mu1, mu2, mu4, everything, you know. Have a look at this. Can't we say here d1 is in vacuum? You can't say d1 is also in the medium, Nare. D1 is the distance between the source and the slits in mu3 medium. That's the reason we're multiplying mu3 na, here.
So we can't do that directly at D1, D2 level.
You can't do that directly. Arre, you are multiplying mu to this distance na. Why will you multiply to d? God.
I thought that would just include it. So
No. You are converting the SS1 into vacuum, isn't it? You're not converting D1 into vacuum.
yes.
With your logic, na, then X will be mu, D1 will be mu, mu will cancel. Not like that. Have a look at this page. It's quite an important question. Once you know what to do, it looks easy. But before that, it looks completely confusing. Like what the hell to do with so many different mediums? Have a look at step by step. Check it out. Ask me if you're confused. Take a minute. This would be a pretty good advanced paragraph question. And you want to mess it up more? I could have kept 2 more slabs here. Not difficult, but you just have to get that and finish it off. Clear with this? Any doubts on this? Take a break. Come back by 9:40. We'll continue from here. Any doubts so far? Chalo, come back in 5 minutes. Let's see one more. So let's say we keep one slab in front of the slit, but this slab is special. X is equal to 0, x is equal to t, the refractive index is not constant. 1 plus x by t. So what happens, you keep a slab whose refractive index is changing, meaning here when you keep x is equal to 0, refractive index is 1, and here refractive index is 2. It is increasing linearly, and it's a thin slab, so d is much greater than t. Find the shift of central maxima. If the slab does not have a uniform refractive index, then what to do? Let's see. Think of like this. At a distance x, take a thin slab, because the formula we derived is for uniform refractive index. So we take the slab to be so thin, I can use the formula for this. So that extra path difference due to dx of, it will be thickness of the slab dx, the refractive index of the slab mu, medium is 1 minus 1. Isn't that the formula? Now the total extra path will be just integrate this. The total extra path will be integral dx, mu is nothing but 1 plus x by t minus 1. Limits will go from 0 to t. This comes out to be t by 2. Straightforward. And what is your path difference? S2p minus, this slab is placed in front of S1, so the path difference will be S1p plus t by 2. This is nothing but dy by capital D minus t by 2. This is your path difference at any point of y. You are asking for central maxima, 0. y is equal to t capital D by 2 small d. Clear? All clear with this? Check it out. So the part difference, right, comes for S1P, not S2P. If the slab had in front of S2, then it would have been S2P plus T by 2. You would have got a minus sign. Matlab central maximum would have shifted downward. So it's important where it shifts. There, that is one part of it. So YDSC and everything. The next thing is thin film interference. Now this in an NCRT, right, it's a pretty straightforward and an easy one. We will see that also, but if you do a small variation, right, it becomes a little tough and it will be a pretty good advanced question. So let's see that one. At a mains level, thin film interference is pretty easy. Again, not something really different. Story is still the same. We need to find the part difference. Do you ever think about this? When people say, na, the size of this thin film is 1 micrometer, 10 power minus 5 meters. How do people measure such small thicknesses? Because if you use any mechanical scale, the thickness is so small, they break. So this is what they do. You send a light ray. Let this be mu, and let's say outside is vacuum. We'll keep it simple. So when the light ray hits an interface, I have shown you this before, you'll always get a reflected ray and a refracted ray. You will get a reflected ray. Then we get a ray inside. Again, we get a reflected ray. Then we get a refracted ray. This would bounce again. So then what people do, we put a lens in front of them because both the letters are parallel. So this letter goes and meets at the focus. This is called a reflection interference because this is happening due to the reflected ray. This is called refraction interference. This is because of the refracted ray. So when you hit this with a light ray, there will be an interference on both the sides of the slab. And if you look at these angles, you'll see why they're parallel. This is I, this is I, this is R. So this is also R. This is also R. This is R. So this must be I. That is how you know it is parallel. This is I, this is R, this is I. Clear with the angles? And let's name them. This is your ray 1. This is your ray 2. This is your ray 3. And this is your ray 4. So we are interested in interference between ray 1 and 2 and ray 3 and 4. And if you look at the phase angles, because of reflection, ray 1 will have a phase shift of pi. This will have a phase shift of 0. This thing I taught you before. This is 0. This is 0. 0. So except that red one, everyone else will have a phase shift of 0. Clear? This is the story. The picture basically the lighters and everything. Have a look at this. This is the main thing. If you understood this, then after this is all geometry only. It's lengthy. It's not really tough, but lengthy it is. Any doubts on this picture? No. So let's name these points A, B, and C. Now, if you look at these two light rays here, the problem is, see, till this point, there's no light ray. The problem starts from point A, isn't it? The whole thing starts from point A. Do you think outside the slab, the red one and the green one are traveling same distance. Look at this. If this was the slab, if this was the red one, and if this was the green one, do you think they're traveling same distances? No, right? If I drop a perpendicular, this and this will be same, agreed? So outside the slab, the red one is actually traveling slightly more. So from this point, see, if you drop a perpendicular, let's call this point D, this is the extra distance traveled by that thing, the ray 1. So ray 1 is traveling AD ka distance outside the slab. And what about ray 2? Ray 2 is traveling inside the slab, isn't it? AB plus BC. This angle is I, this is I, so this will be 90 minus I. This is R, so if you drop a perpendicular, this is also R. So let's calculate these things. So if you take triangle ABE, let's call this point as E. We have tan R is equal to opposite side AE by adjacent side D. AE is equal to D tan R. That means AC is equal to 2 times D tan R. And also cos R is equal to BE by AB. That means AB will be D by cos R. And then in the triangle ACD, AD will be AC sin I. But AC is nothing but 2D tan R. But we know from Snell's law, sin I is equal to mu sin R. So AD will be 2 mu D tan R sin R. Now let's find the path difference. You're finding the path difference. Let's say for ray 1 is traveling AD distance plus lambda by 2. Agreed? Because of reflection, you'll also have a phase shift of pi. So this whole thing I'm teaching you is a theory and the concept basically. This will have a phase 0. If you look at the path difference of the second light ray, you're traveling inside the slab, so it is mu times AB plus BC. This is nothing but 2 mu D by cos R because AB is equal to BC. Therefore, the path difference between light ray 2 and 1 will be 2 mu D by cos R minus AD plus lambda by 2. Check. This part is clear. This is the important thing. The Nietzsche, whatever I wrote, all that is geometry only. I'm just calculating the values of AD and everything. Clear with the steps. Maybe I'll just write this thing as mu times AB plus BC. Yes, we got everything there. Let's substitute the values there. So the path difference between 2 and 1 will be mu 2D by cos R minus AD will be 2 mu D tan R sin R minus lambda by 2. If you take out 2 mu D by cos R common, you end up with 1 minus, that is sin R by cos R, that will be sin square R. That will be cos square R, and then you end up with 2 mu D cos R minus lambda by 2. This is the path difference between light ray 2 and 1. Clear with this. Once you got the path difference for destructive interference, why destructive interference? See, right, whenever you try to observe something, it is difficult to tell exactly when it became bright. But you can always notice when it is completely dark. For example, on your wall, if you see, and if you ask you what is the brightest spot on the wall or which spot of the wall has more intensity, everyone will give different answers. Someone will say this is bright, someone will say this is bright, someone will say this is bright. So there is little confusion there. But if you ask someone which is dark, and if there is a really dark spot, everyone will see that's the same thing as dark. It's like that is the reason when you have a big white wall, it is easy to find a spot on it, isn't it? You ignore that entire white wall and you keep seeing that spot only on the wall. It's like one thing, right? When you wash your face, why do you keep looking at the pimple on your face? The thing is, you have a beautiful face, but we are just worried about that small pimple or that small patch on your face. We have the tendency to look at the dark spots. Getting it? So we are more keen on that. So when you do experiments, generally, we always try to look at the destructive interferences because they're more easy to figure out. Anyway, if I give you constructive interference, you'll put n lambda, big deal. So for destructive interference, delta x will be 2n plus 1 lambda by 2. So this will be 2 mu d r cos r minus lambda by 2 will be n lambda plus lambda by 2. This will give you d is equal to n plus 1 lambda by 4 mu cos r. Now if you take n is equal to 0, then we get d is equal to lambda by 4 mu cos r. That is the thickness of the slab. This is your first minimum. You can just put directly lambda by 2 for first minimum. Clear with this. This is how you find thickness of thin slabs. And look at that. You know lambda, you know mu, and you know r, but everything. This is your thin film interference. But did you get the story here? This thing is clear. That is the main thing. If you got that, then remaining all is just geometry only. Just have a look at this page again if you're confused. And like I said, this is not in the mains portion. There is a simplified version of this. We will see that. But this, if they ask you an advanced paragraph question, that's what I said, rotational mechanics, EMI, AC, wave optics, and modern physics. These are the chapters, where they can ask you really weird things. They can mix up a lot of stuff and they can make really good paragraphs. Clear with this? Now, not only there's one more thing here. If you look at that slab, now just try to look at the difference here. Okay, this was A, this was your C. When you drop the perpendicular distance, this was D. If I do something similar here, this is B, this is F, and if I drop a perpendicular here, let's say this is G. Do you agree this AD and this BG are equal? Same angles. This is I. This is I. This is I. You get the same stuff. Symmetry, no? These all angles are same. So you can clearly see here AD and BG are same. Great. But the difference is this thing has a phase angle pi. This thing has a phase angle 0. This thing is also 0. And this thing is also 0. That means for the refracted rays, if you look at this is coming out. This is BCF, na? So the path difference delta x between 2 and 1, we derived it 2 mu d cos r minus lambda by 2. But if we take path difference between 4 and 3, this will be only 2 mu d cos r. Do you agree with that? Because for the red one, you have an extra path difference lambda by 2 that would be missing. Sure with this? And if you look at these two path differences, you'll notice something. Delta x 21 and delta x 43 are always out of phase by 180 degrees because of the lambda by 2. This will be a good theoretical question. Are out of phase by 180 degrees. What is the meaning of this? The meaning of this is when you take this slab, and let's say we have an observer here. Let's say this is your incident ray. And we have a refracted ray here. If that red person, right, if he says this is bright, so this is the words they will use. They will not say directly maxima and everything. They will say the screen is, the film is brightly illuminated. These are the words they use. The observer feels the film is brightly illuminated. So indirectly saying this is maxima. If this is maxima, because it is out of phase by 180 degrees, then this guy will see minima. So he will see dull film. The whole film will be dull without any brightness. This will be a minima, destructive interference. So basically, if one observer on one side sees maxima, constructive interference, the other guy has to see destructive interference. Vice versa. If the other guy sees destructive interference, if this guy sees dull film, the other guy will see bright. Make sense? And there's a simpler way to remember this. By law of conservation of energy, if one side is maximum, shouldn't the other side be minimum? If you have both the sides maximum and maximum, where are you getting all this energy from? Making sense? If one side you're getting a maximum constructive interference, the other side should be destructive so that the total energy can be balanced. So that's a easy way to remember this, and that would be a more logical proof actually. Here I showed you literally mathematically. So by conservation of energy, if one side is maxima, the other side has to be destructive interference. If one observer sees maxima, the other observer sees minima. And they'll not say constructor, destructor, they'll say bright film, dull film, something like that. Clear with this? This is the actual theory of this thin film interference. And this, what I taught you, is literally the question. Now you can have little variations here and there, but now let's see what is given in NCERT. This is the main thing. You need to remember the result for the main level. So this path difference. So what we do here, 2 mu d cos r minus lambda by 2. If you take the angle of incidence is tending to 0, it's a near normal incidence. Means you're hitting the light ray perpendicular to the surface. If angle of incidence tends to 0, then your r also will tend to 0. Then your path difference delta x would become 2 mu d minus lambda by 2. Yeah, that's your main result there. There is an easy way to derive this. Listen to this thing carefully. So we have the slab here. This is d. This is mu. You're sending an incident light ray here along the normal, almost theta tending to 0. Now, because of this, you'll get ray 1. And because ray 1 is getting reflected, we get path difference lambda by 2. The other light ray will go inside the slab and will come out. This is ray 2. And since you're traveling inside a slab, it will travel mu d and mu d. You can clearly see what is the path difference. The green one is traveling mu d plus mu d. And the red one has a phase shift of lambda by 2 due to reflection. So we get delta x is equal to 2 mu d minus lambda by 2. Easy to derive. That is a proof in this NCRT for a thin slab for near normal incidence. We did all that story for 3 pages to prove this when you put IH tending to 0. So remember this is how you have to do. And for first minimum, at a mains level, general, they'll stick to this only. They won't do all that what I taught you right now. Delta x is lambda by d. We will get 2 mu d minus lambda by 2 is equal to lambda by 2. There, that's your thickness of the film. Clear with this? Let's say a question on this. Again, don't try to remember the formulas. Always try to derive. Because you won't be so lucky, every time mediums won't be like this. I'll show you how they'll go up. If you mug up the formula, they'll do something like this. They will do normal incidence only. So we got a slab here. Thickness is d. Let's say outside is mu is equal to 2. Here this is mu is equal to 4 by 3. And here mu is equal to 3 by 2. This is what they will do. This is even a decent advanced question. I'll mess up the mediums, all the 3 things. And you send an incident ray near normal. Then we got a ray 1. And then we got a refracted ray. They will not draw all this picture. They'll simply say like this. They'll simply say an observer here. The observer on the other side of the screen. He sees brightly illuminated screen. Find D. So the observer is actually seeing the refraction interference. So in the picture, actually, they will not show this. They will give like this only. Now you need to figure out that. I am just drawing that picture for you. Let's see how you do this thing. Let's see. So first of all, if this guy is seeing brightly illuminated, this guy will see destructive interference, isn't it? That is the first thing you need to figure out. Because we are going to study for ray 1 and ray 2 only. This guy sees it as destructive interference. He will think it is completely dark. And that is the first thing you need to realize. They'll mix up like this. If you think that guy sees maxima, you will be gone. Great. Next thing, what about the path difference? Before that, let's define something properly here. Who is denser and who is rarer? Between these two, this is denser. This is rarer. Between these two, this is rarer and this is denser. Make sense? Now for the red one is going from denser to rarer. Do you still think you'll get phase shift of 180? Now you won't get a phase shift of 180. So this delta X, this phase shift will be actually 0. What about the green one? The green one is not only traveling here, mu D, right? It is also hitting here. What is this? Yeah, going from rarer to denser. So this will get a phase shift of pi. Make sense? So what is the path difference now? The path difference between the light ray 2 and 1, the green one is traveling 2 mu D, and it is also traveling lambda by 2 because of that reflection there. That would be minus, and the red one, there's no issue. That's it. That's your path difference. Check. Clear this? Any doubts on this path difference? Got it? But wait. So when you take this, what is this lambda exactly then? This lambda is the lambda inside the slab. Okay. Now these light rays are coming out and you're getting a destructive interference at this guy. So when you say this is equal to destructive interference, 2n plus 1 lambda by 2, what is this lambda? That measures the lambda of the observer, no? You're getting it? This is what I was saying. We get confused with so many lambdas, na? The best thing to do is convert everything into medium. If you convert everything into vacuum, you won't have this problem. This would have been lambda observer. Clear with this? Because if you ask this observer, where are the light rays, what will he say? He will say the light rays are inside the medium, mu is equal to 2. Making sense? Clear with this? I think best thing would be to convert everything into vacuum. Better. That is only better. This is a delta X in the slab. So delta X21 in the vacuum will be mu slab. I think when I wrote 2 mu D slab, na, this thing I already wrote in vacuum. This thing I already wrote in vacuum. The moment you multiplied mu D, you actually converted this in vacuum only. So this lambda slab also I need to convert into vacuum. So let me do one thing. Let's write this as 2D plus lambda by 2 into mu slab. This is better. Where this lambda was the lambda in the medium. You're getting it? Inside, what is the distance travel? D plus D. I think that would be better to write. This is what I was saying. Previously you didn't have this problem because outside was vacuum. If you mess up the medium outside, you will have these kind of problems. So you inside the slab, you travel 2D plus lambda slab by 2. We need to convert this into vacuum. So this is into mu slab. Fair enough. This is your delta X in the slab. By multiplying mu slab, you converted everything into vacuum. Clear? And once they come out, there is no path difference because outside, so they're traveling same distance, so you won't have a problem. You want a minima, so this will be 2n plus 1 lambda vacuum by 2. There, check it out. Okay? Convert everything into vacuum, that is better. Next one. So be careful. That's what I'm saying. Don't mug up the formula blindly. Understand what you're writing. Let's see something more simpler. That will be an advanced question only. Means when they won't touch all the stuff. They won't change the medium outside normally. We have a slab here. This is thickness D. This is mu. Outside is vacuum. You sent a white light. White light meaning you have all wavelengths. And the observer here, for some reason, he can't see some wavelengths. What do you mean by missing wavelengths? So basically those wavelengths must be forming destructive interference. That's why we call them missing wavelengths. Find the missing wavelengths. So when you shine white light onto the surface, some light rays will form constructive interference while coming back, some light rays will form destructive interference. The destructive interference wavelengths cannot be measured. So I mean that it feels like as if they're missing. This is easy. This is a standard one. So this will be delta x lambda by 2. This is inside the slab. This is inside the slab. So this is ray 2. So this delta x will be 2 mu d. So this is a standard one. So the path difference will be 2 mu d minus lambda by 2. You want to find missing wavelength. So this is 2n plus 1 lambda by 2 destructive interference. So this will be 2 mu d is equal to n plus 1 lambda. Lambda will be 2 mu d by n plus 1. If you put n 0, 2 mu d, then 2 mu d by 2, 2 mu d by 3, and so on. All these wavelengths are missing. You know where you have seen this? You must have seen this multiple times. We just don't realize it. Ever seen anything like this anywhere? Oil on a water surface. So when oil falls on a water surface, what happens? It has different thickness at different places. So based on the thickness, some wavelengths will become missing, some wavelengths will be constructive. So for example, look at this picture here. Here you can see blue. Means what? Red is missing. So at that spot, red it is forming destructive interference and blue is forming constructive interference. That's why it looks blue there. So an oil film, right, will not have a uniform thickness. So here, instead of lambda, we will get d ka value. For different values of d, different lambdas are missing. This is an oil layer on a water surface. So that means based on these colors, you can actually figure out the thickness of the oil layer. And you can actually measure how much oil got spilled. It's a technique you can use in order to find how much oil is there on a water surface. There's an oil layer on a water. So next time when you see this, you must have seen this, isn't it? If you drop some oil into the water, you will always see these colors. This is actually an interference. Got it? And there's one more thing, a little interference on a thin wedge with an approximation. So listen to the idea there. This is not a tough one, but you should know how to handle these things. So if you take a very thin slabs, something of this sort. This is T, L is much greater than T. So we are looking something small. I'll exaggerate this figure. This is theta. This is T. So the T is actually very small. So this is your refractive index. This is the refractive index. And let's say if you shine light onto this surface. So how does this work? Again, simple concept, but you should know how this works, nothing else. So when this light hits the surface, there is one interference here, ray 1. The second light ray goes inside, bounces off, and then again comes off. This is ray 2. So at a distance x from here, we take this distance to be x theta and x theta. Since theta is very small, you can assume the light rays are almost vertical. That is an approximation here. The rays can be assumed to be vertical. You can, since theta is small, you can treat them like arc lengths also. And not only that, if you see, this is going from rarer to denser. That means this green one will also have a phase shift of pi. The red one will be in phase only because you're hitting denser to rarer. So the path difference will be 2x theta plus lambda by 2. This will be n lambda for constructive interference. So examine the question was like this: find the number of maximas on the find the number of maximas formed. Then we get n is equal to 2x theta by lambda plus half. So if we take x is equal to L, the length, we get is equal to 2nL theta by lambda plus half. So take the nearest integer. If you got 6.7, then the answer is 6. So basically what is happening is, depending on where you hit, you can have a light ray hitting here, bouncing off, and one light ray like this. If you have this light ray here, this light ray here, you're getting it? So depending on how far you're going, the farther you go from this thing, the more the path difference will be there. So you get different path differences at different points. So there was a question like this in JEE only. Find the number of maximas that will form on this thing. This is the thing that you have to do. So one light ray will get reflected on this surface and one on this surface, and then you do the interference. So just remember this one model. Clear with this? So again, the main thing is your thin slabs. This is your main general thing. What I taught you in, even if you're at an angle, I taught you something even more important. This will be mostly an advanced part. Okay, that would be the last one for the day, and with that we're done with the chapter also. So make sure to go through the whole thing. Like I said, an important chapter. And if you actually think about it, the whole theme of the chapter is this: find delta x somehow. That was the main theme. And there are 3 ways you can find delta x. Make them travel different distances, reflection, or slabs. Today we handled the slabs ka part. In that, YDAC is a part. You're getting it? YDAC is just a experiment in that. It's a special case. And then in that, we saw a lot of variations. Not a tough chapter. You just need to handle some, if you do some 30, 40 problems, you'll get the hang of it. So it's an important one. So make sure to do this. Monday, when we catch up, we'll start off with, after this, actually, we have one more topic in this diffraction. That's the main topic. We will see